I love fencing, but filming it has always been awkward. The piste is long and it's impossible to capture the action nicely from a single camera angle. Someone always has to stand behind a camera to follow the fences up and down the piste. So I set out to build a solution to this problem, and finally say goodbye to the days of awkward filming requests. My first idea was to attach a motor to the central rotating column of the tripod and strap the electronics to one of the legs. However, after discussing this design with my mentor, I quickly scrapped it and started fresh with a cleaner approach that involved mounting the device directly on top of the tripod instead. I wanted the device to operate wirelessly. I debated between using an ESP32 or a Raspberry Pi. In the end, I chose the ESP32 for its affordability and suitability for prototyping. I also considered various motor options and ultimately chose the DSS P05 standard servo motor. Before getting too deep into the hardware side, I needed to develop the tracking logic. Using the Python OpenCV library and the YOLO V5 computer vision model, I wrote a simple tracking program and tested it on downloaded fencing footage. It worked surprisingly well, though it was noticeably laggy, something to revisit later. Once I had the tracking working, I connected it to my motor and microcontroller setup to test them together. Once this was working, I tested on live footage rather than pre-recorded videos. I used a Wi-Fi library in my Arduino code so that the microcontroller could listen for commands over Wi-Fi, while my Python code handled object detection and sent rotation instructions wirelessly. This setup worked well over my home Wi-Fi network. To capture live footage, I installed the Erin webcam app on my phone, which allowed my phone to act as a wireless webcam connected to my laptop. The system worked decently. There was a clear room for improvement. It sometimes struggled to keep up with movement, occasionally overshot or jittered in place. I spent some time tuning the tracking parameters to reduce these issues. Once the tracking was stable enough, I decided to test it at the fencing club with real fences. To do this, I needed to assemble a physical prototype. Using strong superglue, I bonded the bolt directly to the servo horn and left it to dry overnight. It worked perfectly and never came loose. I drilled holes in the top and bottom of the box to attach to the tripod and for securing the servo. I still needed to figure out how I was going to attach the device to my tripod. My first thought was to glue a nut to the bottom of the box, but I realized a simpler, more reliable method was to pass the tripod bolt through the hole in the bottom and secure the box in place with the nut on the other side. Much better. When I brought the device to university for testing, I ran into a new problem: EduRoam. The university Wi-Fi is a protected network that blocks device-to-device connections. To fix this, I modified my code to use my mobile hotspot instead of a Wi-Fi network. This made the system portable and ensured it could work anywhere without depending on local Wi-Fi networks. At the fencing club, the system performed better than I expected, but testing revealed several performance limitations. The most notable was that, in the limited space available, the camera struggled to keep both fences in frame. The Erin webcam only supported one-time zoom, so I explored alternatives. Eventually I found IVCam, which not only supported 0.5 times zoom, but also worked perfectly with a hotspot connection. Exactly what I needed. While my cardboard box prototype worked, it looked rough and had several practical issues. While my power bank fit in the box, the cable did not. The bolt heads on top of the box would also interfere with the phone clamp's rotation. I knew I needed to upgrade the housing. On my mentor's suggestion, I bought a black electronics enclosure, which turned out to be the perfect size. I also replaced the original bolts with new ones that matched the housing color and had smaller heads, preventing interference with the phone clamp. After carefully measuring, I drilled new holes for the servo and tripod mount. The housing wasn't tall enough to fit the entire servo and bolt, however, so I filed the hole until it was large enough to allow the bolt to extend slightly out of the top. This adjustment not only solved the height issue, but also created extra clearance for the phone clamp. I brought the refined version back to the fencing club and spent several sessions optimizing and fine-tuning parameters until the tracking was smooth and reliable. By the time of the MakerLab showcase, the final build worked exactly as I'd hoped. It tracked both fences reliably, rotated smoothly, and had a clean, portable design. Through this project, I learned that iteration and feedback are everything. The final design is simple and elegant precisely because I went through all the messy, imperfect versions first. Next, I'd love to expand the device's capabilities by adding zoom and tilt functionality, automatic scorekeeping, and on-device AI so it can operate independently of a laptop. But for now, it's a solid proof of concept that brings together AI, control systems, and design, all in one neat little box.